everyone. Let us start our discussion on this subject, that is underground space technology. So, this is the first lecture in which we will be discussing about some of the basics of rock engineering. So, what I will do is, in the beginning I will tell you what all are the topics that we are going to discuss in this subject, followed by some of the reference material, and then we will have some discussion on the basics of rock engineering, including introduction, spherical representation and physical properties of intact rocks. So, to start with, let us discuss that what all are the topics which will be covered in this course. So, the first one is that we will take up basics of rock engineering. This will include the description with respect to rocks and rock masses, their physical and mechanical characterization, along with the classification and the failure criteria which are applicable to the materials like rocks and rock masses. Then we will discuss about the planning of underground excavation, that what all are the criteria that one needs to keep in mind while going for planning of any kind of underground excavation, whether it is tunnel, cavern or things like that. Then we will learn some aspects related to stereographic projection method. We will learn about its principle and the application in the underground excavation design. This will be followed by the elastic analysis of underground excavations, and in this one first we will learn about the in situ stresses. Then we will also see that how the stress distribution around the tunnels can be obtained. This first we will start with the circular tunnels, and then we will go to the different shapes of the tunnels, for example elliptical, ovaloidal or say square shape tunnels, and in this context we will learn this Greenspan method. Then we will move to the multiple openings, because in many situations you may have more than one opening. So, how to analyze that using the theory of elasticity, that also we will learn. And then in most of the cases you may not have the uniform strata of the rocks. So, in case if you have laminated rocks, then how to go ahead with the elastic analysis of openings in laminated rocks, that we will discuss. Then we will move to the elastoplastic analysis of tunnels, and in this one we will take two types of yield criterion. One is Tresca yield criterion and another is Moore Coulomb yield criterion, and using these two criterion we will see that how the elastoplastic analysis of tunnels can be carried out. Then we will learn about the application of rock mass classification systems such as RMR system, Q system, Terzaghis rock load theory, and also we will learn about various ground conditions in tunneling. Then we will go to the openings in squeezing and swelling ground conditions, and we will learn about the support pressures, deformations and the modulus of deformation. This will be followed by various in situ tests which are conducted in the field for determination of modulus of deformations. These include uniaxial jacking or plate jacking tests, plate loading tests, radial jacking test and Goodman jacking tests. Then we will discuss about the tunneling methods. Basically these are not the methods but the philosophies. So, we will take up these two methods, that is New Austrian tunneling method and Norwegian tunneling method, that we call in short as NMT. After we get this much of the foundation related to the underground space technology or the design of underground excavations. Then we will take up the topic which will deal with the rock mass tunnel support interaction analysis, and in this one we will first discuss about the phenomena of this interaction. In this context, we will learn about the ground response and support reaction curves, and then we will go ahead with the elastoplastic analysis of tunnels considering this interaction, and this is called as Ladani's elastoplastic analysis. Then we will discuss about the design of various support systems such as shotcrete, maybe the steel sets, rock bolts, etc. Once we know this, then we will learn about various tests for the determination of in situ stresses. These include flat jack tests and hydraulic fracturing, and then we will go to the instrumentation and monitoring aspects of underground excavations, and this will be followed by finally some of the case studies which I will be discussing with you, that how whatever knowledge that we gain throughout the journey of these 12 weeks, how these were applied to some of the case studies in solving some typical problems related to design of underground excavations. So, the source material is going to be the relevant chapters from various textbooks on underground excavations and rock engineering, plus the relevant Indian standard quotes. Then we will be referring to various documents which are available in public domain, and of course many images through public domain research, they are going to be used, and we highly acknowledge these sources. Apart from these, I will be discussing with you time to time, if let us say we discuss or we refer to any research paper with reference to any of these theories or topics, that I will keep sharing you with time to time. Now, some of the books that I have mentioned here. So, first book is by Obert and Duval. Here is the reference. Then this is the basics of the rock mechanics, so by Goodman. Then very important reference by Hook and Brown, and the title is Underground Excavations. Then one of the basic book on the rock engineering and rock mechanics, that is by Ramamurthy, that is Engineering in Rocks for Slopes, Foundation and Tunnels, and then the book which deals with the engineering rock mass classification by Singh and Goel. Now, once we know that what all things that we are going to discuss and what all are the references which we will be following, let us first take a look about this material called rocks, and that will be followed by rock masses. So, first we will discuss few aspects related to this. Please remember that this is a little bit advanced course, so we will not be going into the details of the basics of rock mechanics and rock engineering. However, to have the completeness, we will be discussing some aspects, and then we will directly go to the elastic analysis of the circular tunnels. So, to start with, these rocks are geological materials, and these are granular, heterogeneous and anisotropic, and these consists of two components. First one is the mineral grains and another one is glue. So, basically mineral grains, they are crystalline in nature, maybe polycrystalline or can be non-crystalline, and the material which binds them together is under this category of glue material. These may have the properties like ferruginous material, calcareous, argillaceous and siliceous material. Now, what happens when there is a bonding between mineral grain and glue material? Then we get the material rocks. Now, which type of bonding should be there. So it can be the mechanical bonding or atomic bonding, ionic or the molecular bonding. Now these bonding should be within mineral grains, within glue, and at every interface of bonding. So with the bonding of mineral grains and glue type material, the resulting material is rocks. Now coming to the rock mass. So when these rocks, they have various discontinuities, then that material is called as rock mass. Now what do we call that as discontinuities? These can include micro cracks or fissures or voids. These can be called as joints. Of course, these joints are defined by dip, dip direction, strike, their spacing. There can be geological faults. The discontinuities can be in the form of shear zones or thrust zones. So here I have added very interesting picture of sugar cubes. These are the smallest size of the block of rock mass. Okay, so we see this thing on day-to-day basis, but then we never realize that what it can be. So that's the most simple example of a rock mass, that is a sugar cube. Now the mechanical behavior of rocks and rock masses, they are entirely different than that of the soil or concrete. The reason is you have seen that it is the mineral grain and the glue material binding of these two at different levels that results to this material rock, and when there is a discontinuity that is present in the rock, we get rock masses. However, in case of soil, it is altogether different, and concrete is a man-made material. So the mechanical behavior of rock and rock masses, they are completely different. It's not that this engineering or this technology is very new. There are many structures which were constructed in rock masses. So here some of the typical pictures that I have downloaded from Google just for your reference. So here this one, if you see, this is the picture of the big temple in Tanjavur. Okay, so like that all over the world you have many structures in rock masses. So it is not some engineering or the technology which is new. What are the field applications? Okay, so right now we discuss with reference to rocks only. So there can be various applications. For example, you have to go for the large dam construction which is founded on the rock masses. So these may be anisotropic, that is they do not have the same property in different directions, and then you can see that there is going to be the presence of the vertical load as well as the horizontal load. So this is founded on rock masses. Then you come across various landslides. So there is the rainfall, and then it triggers the sliding of this material, you see, in this particular direction. So here you may have soil bed or you may have rock bed. So that is also one of the application of this rock engineering. Then you have the construction of bridges which may be founded on the rock masses having various discontinuities in the form of joints or bedding planes. So this is another application areas. Then we have the tunnels. So you see that this area, which is this one, is the rock mass, and we make an excavation which is this portion. So when the excavation is made, what happens to this boundary? This boundary becomes stress free. The moment it becomes stress free boundary, there is going to be the redistribution of stresses, and this will result in the differential stresses. So, before the excavation there were the presence of in situ stresses, say in the form of the vertical stress sigma v and horizontal stresses sigma h. But the moment you create the opening, you have a stress free boundary and the stress redistribution has to take place. So, that is another application with reference to rock engineering. Then we have the nuclear waste repository and the open cast mines also as one of the application of the rock engineering. So, we have seen that discontinuities are important, and when the rocks they have these discontinuities, it becomes the rock mass. So, the question comes that how to represent these discontinuities or any geological data that is present, maybe in the form of shear zone, thrust zone, like that. So, let us see that how these can be represented spherically. So, we have the discontinuities, these include bedding planes, faults and joints, and it is important to define the orientation of these without any ambiguity. So, the terms which are used include dip, which is usually denoted by the angle psi, then dip direction denoted by alpha, and strike. Now, this figure is self-explanatory to define you the various terms which have been mentioned here, that is dip, dip direction and strike. So, you can see that the plane has the dip with reference to this strike line, and hence this is the angle that is psi, which is given by or which represent the dip. This angle or this dip direction is shown here. So, in case if you want to learn in detail about these terms and how these can be determined, you can refer to this link where the details have been discussed. Now, when we deal with the axis of a borehole or a tunnel or the intersection of two planes, these are lines and not the planes. So, the orientation of a line is denoted by plunge and trend rather than dip and dip direction, which was there in case of planes. So, plunge is basically a term which is similar to dip. This is the inclination of line to the horizontal, and trend is the term that is similar to dip direction, which is the direction of horizontal projection of the line that is measured clockwise from the north. For more details, you can refer to this link. Then coming to the various laboratory testing of rocks. So, basically strength, modulus and stress strain relationship of rocks, these are influenced by their mineralogical content, the extent of pore and presence of the pore fluid, which is more often water. So, based upon these conditions, the question is how to determine the strength and the mechanical characteristic. So, for this we take the sample from the field, bring it to the lab, and then we carry out various tests. So, basically what we do is we get rock cores from the field, and these are subjected to various tests in the lab in order to determine their mineralogical composition, physical properties and engineering properties. Let us try to take a look. So, for the mineralogical studies, we carry out the micrographic tests for petrographic description of rocks to indicate its mineral content, grain size, texture, fabric, degree of weathering and porosity. So, what we do is we make a thin section of rock and then we carry out this test. So, as far as civil engineers are concerned, yes, we conduct these, but many times we rely on to the experts from earth science stream because they have the better insight about these mineralogical content as far as rocks are concerned. Coming to the second category of tests, that is determination of bulk and saturated unit weight, water content, porosity and void ratio, degree of saturation and specific gravity of rock grains. You have studied these terms with reference to soil mechanics. So, the definition remains the same. So, we will see in short that how we define these once I discuss about the third category, which include the engineering properties. So, under this category, the first test that we conduct is the unconfined compression test, and this is conducted to obtain the compressive strength, elastic modulus, Poisson's ratio and also the complete stress strain response including various modes of failure. Then the second category is the determination of the tensile strength using Brazilian tensile test. This is an indirect test where the specimen is subjected to the compressive load, but what we get is the tensile strength. Then the third category is shear test, in which we obtain the shear strength parameters on joints with or without gauge material. Now, what is this? See, in the field you have the rock with joints, that is you have the rock mass. Now, if by some way or other if these joints get open and if they are there for longer period of time, what happens is this gauge material, which may be of let us say clay type of material, it gets deposited in that joint. So, those joints they are called as joints with gauge material. Then we have another type of shear tests, which are triaxial tests, which help us to obtain the strength envelope. Then shear strength parameters of chosen failure criterion, stress strain response, how the modulus is varying, what is the change in the modes of failure when we increase the confining pressure. You all know that the triaxial tests they are conducted at different values of the confining pressure. So, what happens if we increase the confining pressure, there may be the change in the mode of the failure. So, by conducting this triaxial test, we will be able to get all these information. There are various other tests apart from these which also help us in getting some of the engineering properties of the rocks. So, one such test include point load strength index test. This helps us to obtain compressive strength and the tensile strength of regular as well as irregular rock samples. Then the second one is the slag durability test. It helps us to find out the resistance of the rock samples to disintegration when these are subjected to specified cycles of wetting and drying. Then we have the sound velocity test, which we conduct by the propagation of elastic wave. These can be P wave or S wave, and this helps us to find out the dynamic elastic constants such as modulus of elasticity, modulus of rigidity and Poisson's ratio of rock cores. Then we conduct swelling tests on regular rock cores. These are conducted to assess the extent of free swell upon saturation and also the swelling pressure of rock upon saturation under non-swelling condition. Then the last test in this category, special tests, that is Schmidt rebound hardness test. This helps us to find hardness and also the compressive strength of the rocks. Now coming to some of the physical properties, as I mentioned to you that you are aware of these with reference to soil mechanics. So the definition remains the same. For example, when we say that dry unit weight, so it is represented by gamma d, that is weight of grain of the sample to bulk volume of the sample, and its unit is kilonewton per meter cube. Then the next one is the water content. This is always represented in the percentage, that is weight of the water divided by weight of the solid. Then the third term is volume of the solid grains, that we have as a dry unit weight, that is gamma d, upon the specific gravity of the grains, that is g. Then volume of voids is 1 minus the volume of the solids. Then void ratio is defined as volume of voids by volume of solids. Porosity again represented in the percentage, and this is defined as volume of voids by the total volume, and then you multiply that by 100 in order to represent it in percentage. Then we have the moisture content at 100% saturation. So that is, you remember we have ES equal to GW. So when we have the 100% saturation, so this S becomes equal to 1. So this will result into E is equal to G into W. So if we want to find out the moisture content at 100% saturation, so here it is Ws. So that is how you are getting this expression, that is E, which is void ratio, divided by the specific gravity, E by G, and since it is represented in percentage, so I multiply this by 100. Coming to the next definition, which is the degree of saturation, that is again represented in percentage, volume of water divided by the volume of voids. Once we know the dry unit weight gamma d, we can find out the bulk unit weight using this expression, where small w represents the water content, and then we can also find out the saturated unit weight. Please remember that here we are finding out the unit weight, and therefore the unit is kilonewton per meter cube. The unit for density is not kilonewton per meter cube, but maybe the gram per cc, okay, or kg per meter cube. So that is a difference between density and the unit weight. Density is mass per unit volume and unit weight is weight per unit volume. Then there is a relationship between the void ratio and the porosity, which is given by this, where N is the porosity and is represented in percentage. So G, as I mentioned to you, is the specific gravity of grains. So here we learnt about the introduction related to the material called rocks and rock masses. What all are the various tests to determine the physical and the mechanical properties of the rocks in the lab. So in the next class, we will learn some aspects about preparation of specimen and the conduct of unconfined compressive strength tests in the lab. Thank you very much.